Bueno, y la próxima charla que la vamos a tener desde Australia está a cargo de el doctor Julius Van Der Werf, Andrew Swan y Daniel Brown de la Universidad de New England en Armidale, Australia. Y la charla se titula Presentación y rol futuro del mejoramiento genético en la competitividad del sector lanero. ¿Sí? La van a tener proyectada, pregrabada.
Julius Van Der Werf from the University of New England in Armidale in Australia. And you can see on the background here where we live. I would like to thank the organizers for inviting me to this symposium, and I'd like to share the screen with you and show some slides about my talk. So my talk is about the role and orientation of animal breeding in the competitiveness of the wool industry in Australia. And my co-authors are Daniel Brown and Sam Walcom, and from Egbu, and Peter Bradley from Sheep Genetics. So I want to talk about three things. First, very briefly about the Australian wool industry and where it stands now. Then on the role of genetic improvement and how important it is in that industry. And then I want to talk about some new developments and future objectives that we have in mind. So the Australian wool industry is produces about 335 million tons of greasy wool. Last year, it had a value of about 3 billion Australian dollars, which is equivalent to about 2 billion US dollars. So we produced that with about 70 million sheep. 70 million is the total of merinos, maternals, and terminals. But generally, the merinos are the ewes that produce either the wool or the lambs when they're crossed with terminal sires. So they make really the majority of the ewe flock that we have. Of that wool, 2/3 is quite fine. It's smaller than finer than 20.5 micron. And within that segment, 30% is smaller than 18.5. So we have a fairly fine wool industry, but also quite a significant part that focuses more on broader wool and dual purpose and also lamb production. So importance of genetics in the industry, as you know, we've moved gradually from selection based on looks to selection based on measurement. So, and especially in the merino industry, there's still a large tradition of selecting based on looks, and it has taken a longer time to move towards more objective measurement of traits and genetic evaluation and prediction of breeding values, as compared, for example, with the meat sheep industry. An example of what can be achieved with a proper genetic improvement program is shown with this slide. It shows the meat industry in Australia, which was kind of the poor cousin of the wool industry, started to really work on genetic improvement about 3 decades ago, and they've increased the main trait, which is the carcass weight, by about 28%. And as a result, the carcass price has almost tripled. And that increase is partly because of the product being improved. It was easier to get export markets. There was more demand for the products, and therefore not only increasing the amount of meat that was produced, but also the price that we got for it. So overall, the value of the industry has increased by about 5-fold in the last 3 decades. In general, in sheep in Australia, we do genetic evaluation via Sheep Genetics. It's a subsidiary of the Meat and Livestock Australia company, and Australian Wool Innovation was initially part of it and now not formally part of it. So the idea of the Sheep Genetics is that they collect measurements on farm by stud breeders that send their data via the internet to databases. Then centrally there is a genetic evaluation with millions of animals, and the result will be Australian sheep breeding values or estimated breeding values sent back to the breeder. So this system was put in place for the lamb industry in the 90s, and then for the wool industry in Australia about 20 years ago in about 2005. So the merino industry works with those traits roughly. So they relate to wool production, but also to meat production. So we measure body weight, fiber diameter, fleece weight, staple strength, curvature, worm egg count for the parasite traits, breeds and body wrinkle, which are becoming increasingly important because we want to select against strong wrinkle to avoid the need for mulesing. We look at fat and muscle for the lamb production because a lot of ewes are across this terminal sires, and reproduction has become more important as well because of that same reason. We also have the possibility to select for polled and horned with a very predictable DNA test. So those traits are measured at several ages, so that the total number of traits in the evaluation is close to 60, but they are summarized in indexes that people can use to select their animals from. And those indexes are either based on fiber production, that they're focusing on fiber production for the fine wool segment of the industry. Merino production are a bit in the middle, and the dual purpose indexes are focusing more on the lamb production, where wool is not the main source of income. The participation in genetic evaluation has increased a lot over the last 2 decades. So the animals recorded, you see a graph here, has improved from 40,000 to 150,000 per year. And the number of flocks that we're evaluating has increased from 170 to 400. So in the merino industry, about 50% of all rams sold would have figures on them in terms of breeding values, which is a lot lower than in the meat industry, where we have more than 90% of rams having figures like that. But certainly in the merino industry, the numbers are increasing, and the number of animals with genetic merit predictions is increasing rapidly. So this slide shows that the merino industry and Merino Select, the number of flocks was very small even 10 years ago, and that has increased already quite a lot, and is creeping slowly towards the number of flocks that are evaluated for lamb plan. Also on this slide you can see that the genotyping is increasing a lot. So the dark green lines are genotyping for prediction of breeding value. We call it the genomic test, and that started about 10 years ago, but that has in the last 4 or 5 years increased rapidly, and now we're genotyping more than 120, 150,000 animals per year. Half of that would be merinos. And the parentage was initially very popular, but it has decreased a bit, and that really has been taken over by the genomic prediction DNA testing. And the reason for that is partly because the difference in price between parentage testing and genotyping for genomic prediction is not that large anymore, so you might just as well do a full test. So in the merino industry, we've achieved quite a bit of genetic gain for the key traits, as you can see here. So live yielding weight and eye muscle have improved quite a lot. The wool, the greasy fleece weight has improved by about 12%. The fiber diameter has deteriorated slightly, so it used to be a bit finer than it is now. And that probably has to do with the direction of the industry going a bit more towards dual purpose and lamb production, and more animals being part of that segment. We've also made progress in worm egg counts and parasite resistance, and we have made progress in weaning rate of the number of lambs that are weaned per ewe. It's in the reproductive performance. So the main developments that we deal with at the moment are in genomic selection that's introduced and widely applied, and the potential that has. And also the objectives, the breeding objectives, and which traits to emphasize in selection. And also that is changing gradually, so I want to talk mainly about those 2 topics now. First, genomic selection. So as you know, before genomic selection, we could look at the animal's performance, and we could also use some information of relatives, like the sire and the dam and some siblings, to make a prediction of genetic merit. but there's only a limited number of animals that inform the genetic breeding value of an animal. With genomics, we can widen that range of animals that we use a lot more, because a DNA test of a young animal now can be linked to DNA tests of thousands and thousands of other animals that have been genotyped and that have performance traits measured. So we have now access to a lot more what you could call relatives, but they are slowly related maybe, but because there are so many, it provides a lot of information. And more importantly, we can measure those animals for traits that usually cannot be measured on breeding animals, such as slaughter traits or traits that are difficult or expensive to measure, such as feed intake, and even reproduction, which cannot be measured on rams. It can be measured on lots and lots of ewes that would predict the breeding value of a ram very early on, which is good for making genetic improvement. So we call this the resource flock, or more general, the reference population for genomic prediction. And we've emphasized and invested quite a lot in the resource flock in Australia in the last 2 decades. So the effect of genomic information for a breeding program means we can now use information on many more animals that we could call far distant relatives, but because there's many, we can that really is useful information for predicting genetic merit, and we can measure those reference population animals for a lot of traits that we would previously not have much information on and that were hard to improve. So we call them, in general, hard to measure traits. So reproductive performance is hard to measure because you cannot measure it on males. Parasites is not an easy trait to measure because it's a lot of work. So if we concentrate measurements on a resource flock, that would be useful. And meat eating quality and slaughter traits, of course, cannot be measured on breeding animals. In the wool area, lifetime wool is an important trait. Like we can measure early wool, but not later wool. And we want to select animals as soon as possible to make a lot of genetic progress. But we have to wait too long before we have enough information. So again, if you have historic animals with that data, you can use that for selection and prediction. And more importantly, new traits such as methane output and feed efficiency are really hard to measure by breeders, but you can measure them centrally in a resource flock, for example, at a research station, and in that way create a reference population for genomic prediction of breeding values for such traits. So we started with resource flocks in Australia in 2007 in the sheep CRC. We called it then the information nucleus. So it's a whole set of animals that we measure for traits and new traits to estimate parameters, but more importantly, to have a reference for genomic prediction. So in the first 5 years, we measured about 20,000 lambs and 10,000 of those in detail for meat traits, and the others, including about 4,000 for reproduction and wool traits. So that was a very successful start, and MLA decided to fund that since 2012 as the MLA resource flock. So we measured in 6 years about 12,000 lambs for meat quality and eating quality. So we measured the quality of the meat and the eating quality of the meat. That project was again extended in 2019. Again, 2,000 lambs per year measured, so a total of 10,000 until next year. But also we included commercial producers that wanted to slaughter their lambs, so we helped them by genotyping and assisting them to get that data. So that's a cost-effective way to get more data from the industry, where you engage with commercial producers to collect information and genotypes on animals that they slaughter anyway. And also we engaged with people that measured reproductive performance on animals. So we would pay for the genotypes, and they would provide the phenotypes for reproduction. Again, it's a quick and cheap way a relatively cheap way to make a reference population for genomic selection. And now we also use information from an AWI project on merino lifetime productivity, where 5 ewes are measured for 5 years for lifetime wool performance as well as reproductive performance. And reproduction is a low heritable trait, so you want to collect lots and lots of information, lots of animals measured for a good reference. So the resource flock that we run for MLA is about 30% pure merinos, and the rest is crossbred, so the mother is usually merino and then either mated with a maternal or a terminal sire. And the traits measured are the usual life traits like growth rate and ultrasound scan for muscle and fat, but also parasites and horns and carcass traits such as such as yield and eating quality traits such as intramuscular fat and tenderness. And we also have eaten a lot of those animals and have consumer scores, so we can actually validate whether those traits predict eating quality. So the new traits we're going to measure in those resource flocks are methane yield and feed intake. So we've started with methane yield already this year, and we're still building facilities for measuring feed intake, but that will start next year. So this is a little picture of how you can measure methane. That's a trailer with it has 12 boxes on it, and in each of those boxes we can put a sheep, either a lamb or a ewe, for a bit less than an hour to measure how much methane it produces, and we observe a lot of variation for animals that actually are running under the same diets. So there's variation in methane yield, and we can select for that. Methane yield is very related to how much you eat, and therefore it makes sense to measure feed intake as well in the same animals. And we try to target animals that have already lots of information on other traits, such as reproduction. So, for example, we measure ewes from the Merino Lifetime Project, or animals from the resource flock that have been measured for meat traits, so that we can estimate correlations between those new methane traits and the existing production traits. So the pipeline that we have to generate breeding values can easily be enhanced, because if we measure new traits like methane and feed intake, we just put it through the same pipeline, and we can do genetic evaluation and provide breeding values for breeders that can make selection decisions based on those new traits. So what do they actually want to achieve? What are the objectives in the industry for the merino breeders? We didn't have a review of indexes that are being presented at the moment to the merino breeders, and we workshopped with them what traits they found important and whether the current indexes actually do what they want. And the result was a bit disappointing, because it turns out that the indexes are not used a lot. Most people think indexes are not really for what I want, and there was a demand for an update of them. One aspect that was under-evaluated, they thought, was that there needs to be a lot more emphasis of selection for wrinkle, because the fly strike of wrinkled sheep is a problem, and it will be less and less possible to apply mulesing, because the consumer will not accept that. And the other demand was for resilience, that sheep that do well even if conditions are a bit weak in terms of feed availability. For example, if there's a drought and feed is very expensive or not available, then we don't want the sheep to die too quickly. And there's variation in how well sheep can deal with those circumstances in terms of how well they keep condition score and can store fat. So those are some new traits that they want to look at, and there's some research going on and some initiatives to improve the indexes. So overall, the industry is looking for increasing productivity, but also improving animal welfare as a social license to produce seed products, and to make farms resilient to the varying climate conditions that we experience due to climate change. So we have periods of drought and then periods of a lot of rain, and we want sheep that can be held under all conditions. So the index changes in the merino industry for this year will be that, first of all, we update the models and better account for the feed costs of animals through the year. The reproduction traits will be split in three. So the trait we used to have was weaning rate, how many lambs does a ewe wean? But that's really the result of three underlying traits, and those are the traits: fertility, like do you get pregnant, litter size, how many lambs are you producing, and maternal ability, like how well do you make the lambs, do they survive birth and do they make it till weaning? Because the lamb survival is still often around 80%, and that's really low. So they want more, the new indexes have more emphasis on wrinkle and DAG score and also on parasites, because farmers really want low maintenance animals that do not die and that survive well but also produce well. And then resilience is captured by condition score and breeding rates for fat and muscle at different times of the year. So how well do they keep their condition? And again, there's genetic variation in those traits that can be selected for. A few more words about selection for methane efficiency. So we have a project called Selection for More Methane Efficient Sheep. And we all know about the effect of ruminant productivity on greenhouse gas emissions, and so we're expected to do something about that. Now, genetic improvement is a very slow way to do something about it. As you can see here, we're producing in Australia currently 18 million megatons of CO2 equivalent, and maybe by 2040 you can reduce that to by at most 10% or so. So maybe reduce it to 15.8. So that's not enough to get rid of the methane gases, but it's at least it helps towards many ways to mitigate emissions. So genetic change is a slow process, but at least it's permanent. So once you change animals, you don't have to do any, invest new things into them. And it's cumulative, so every year you make small steps further towards your goal. So you can contrast that with other ways to mitigate greenhouse gases, such as feed supplements. They are usually very effective in reducing methane, but of course they cost money. So you have to keep investing in it if that's your only solution. And this graph from Rob Banks shows that if all animals would need feed supplements to reduce greenhouse gases, you'll have a cost up to 2 million for the industry, and that you have to spend every year, whereas it's 2 billion actually. And so depending on how quick that is introduced, it will take a while maybe, but once it's used, it reduces greenhouse gases, but at a large cost. Now, the curves that go down here show the same scenario where you also do genetic improvement. So if you do genetic improvement, you can actually reduce the cost of mitigation due to other things like feed supplements. And that's really the long-term value of genetic improvement. So how do we select for methane emission? Well, we want to have more methane efficiency in terms of less methane per unit of product that we try to produce. At the same time, we want to improve productivity, and probably a lot of the methane efficiency is achieved through productivity increases, as we'll see in a minute. So to work on methane, you have to look at the system and the system efficiency in terms of lambing rates and what diets you use and what systems and crossbreeding systems you use. But within those systems, you can also select for individual animal variation in how much methane they produce in relation to how much feed they eat, in relation to how much they grow, how much wool they produce, how much lambs they produce. So we look at the production traits and correlate them with the trait called feed efficiency and methane efficiency. And we want to see what is the best strategy for improving those. So how important is it to select for variation in methane output? Or do you do that maybe already by improving the system efficiency? What is the trait that you want to measure? Is it measured on lambs, on ewes? And is it measured in feedlots or in the pasture? And in Australia, roughly most of the methane is produced by ewes, and most of the diets are on pasture, so that's probably the most dominant environment where you want to measure it. So do we want to decrease the methane per animal, or do we want to optimize the amount of methane produced per unit of products? Or do we want to maybe decrease the methane per kilo of feed eaten? There's different proposals that have been shown in literature how you can select for methane efficiency. I am going to promote methane intensity, which is really reducing the amount of methane you need for the product that you produce. So we did some modeling and first looked at the economic values, which is how important is it to change those traits? How much emphasis do you put on those traits? You see there's high economic values for fertility, but that is also related to the units of the trait. So you cannot really compare the economic values of traits within a column, but you can compare them between columns, because I'm looking here at 3 different objectives. The first is to maximize profit. The second is to reduce the methane output of a flock of a fixed number of ewes. And the third is to reduce methane per kilo of lamb that you produce. And you could have a similar story for the kilo of wool that you produce. So this is methane intensity, is reducing methane per kilo of output. So if you select for maximizing profit, then all traits have some value, and the red ones have a negative value. So for example, you want animals to eat less, to produce less methane, and to have smaller, finer fibers, and all the other traits should go up. If you were to select for animals that produce less methane, then you of course put a strong negative value on methane production, but you would also put a negative value on reproductive rate, because per ewe in your flock, if they have fewer lambs, then overall you produce less methane, which is of course counterproductive, but that would be the best economic weighting for traits that affect overall methane output. If you want to reduce methane per kilo of lamb produced, you still want to work on the growth rate of lambs, because the faster they grow, the quicker they are gone. And you also want to improve the reproductive rate, because the more lambs per ewe, the fewer ewes we need to produce the same amount of lamb meat, and therefore we reduce the greenhouse gas through improving reproductive performance rather than methane itself. And of course you would put a negative value on methane as well. So the next slide shows that what those 3 different sets of economic values would deliver in terms of economic change, genetic change in the flock. So I'm looking at a few traits, and I realize it's quite a few traits, so let's look at some main points here. But those are the current means of traits, and this is how much change you can achieve in a few years. And we see that lambing rate usually goes up, because you select for more reproduction, and growth rate goes up. But if you selected for lower methane, then lambing rate would go down, growth rate would go down, and feed intake would go down. That's because all those traits are correlated to methane output. And so it really shows that it's not a good idea to select for animals that produce less methane, because they will be a lot less productive, and you would lose. So with a normal breeding program, you can gain $7 of profit every year. But if you selected for low methane emitting sheep, you would lose $6 of profit every year. And overall, you're not even becoming more methane efficient, because if you look at the last line, how much CO2 equivalent, how much greenhouse gas do you produce per kilo of lamb produced? So compared with the current situation, if you select for more profit, you reduce that by 3%, which is it's good to reduce it. But if you select it for animals that produce less methane, because they also lose productivity, the overall methane efficiency actually goes up and deteriorates. So you produce, at the end of the day, more methane per kilo of lamb produced if you would select only against low methane. So the ideal solution is probably somewhere between column 1 and column 3. This is more profit, this is methane efficiency per kilo lamb. Both give a similar profit improvement, and they give also a similar reduction in how much methane you need to produce a kilo of lamb. So in summary of that methane work, I'm showing that we are trying to provide tools for breeders to select for low methane emitting sheep, but they would use that in an index alongside other production traits. So genetic gain is one of the solutions to mitigate greenhouse gases. It is permanent and cumulative, but it's it's slow, but on the longer term, it's a very valuable thing to do. So we develop reference populations or resource flocks that measure methane, such that we have a base to predict breeding values for those traits through genomic selection. The economic modeling shows that it's not optimal to reduce the methane per animal. What is optimal is to improve productivity and at the same time select for animals that, given that extra productivity, produce less methane. So it's a similar thing as if you want to improve your feed efficiency, you would not select animals that eat less. You would select animals that eat less relative to the extra growth. So efficiency gains are not selecting directly against the trait. You have to look at all traits that affect efficiency. And in particular, reproductive performance. If the reproductive rate is higher, we need fewer ewes to produce meat, for example, and therefore it's an important trait to improve methane efficiency. So in conclusion of what I talked about today, it showed that the Australian wool industry can benefit a lot from genetic improvement, and it increasingly uses estimated breeding values for selection. Within that, the use of genomics is now widespread, and the reason for that is we can now select for traits that are hard to improve otherwise by looking at the animal itself. But a lot of those hard to measure traits are important in how we want to improve our sheep, especially reproductive performance, meat quality, and also methane efficiency and feed efficiency. So in the indexes that we use, we want to put more emphasis on reproductive performance, as well as select against wrinkle, against parasites, and for more resilient sheep. So we want sheep that maintain condition score. And we want sheep that are sustainable, good for sustainable production systems and produce less methane. So that's my final slide. Thank you for your attention. And I just want to acknowledge some co-authors from New South Wales DPI that help us a lot in the methane project. Sheep Genetics, who we actively work with to implement breeding values. Pete Fitzgerald also working in the methane project, and the Egboot team that produces breeding values and who we collaborate with very closely. Thank you very much and hope to answer some questions.